Hello, class. Our names are Andrea, Celeste, Pachada, and Astrid, and today we'll be focusing on a presentation on thermal protection systems.
To start off, what are thermal protection systems? Thermal protection systems are put in place because of the extreme thermal environments when re-entering the Earth's atmosphere. Spacecrafts need a shield to protect them from this harsh environment, which is what the thermal protection system is. The thermal protection system absorbs and reduces the heat on the spacecraft. In the bottom here, you could see on the left image that this is a black shell tile panel from NASA. And on the right, we also have a spacecraft with Orion components from NASA as well. So, why is it important? An effective thermal protection system will do its job to protect the humans' lives that could be on the spacecraft. Furthermore, thermal protection systems allow for successful space missions and enables a controlled return of spacecrafts back into the Earth where data could be collected to use. In the right, there is an animation of Artemis 2 from NASA as well. Robert Goddard developed the concept of a heat shield in the late 1920s after observing the behavior of meteors entering the Earth's atmosphere. Around World War II, various countries tried to create long-range missiles and rockets capable of leaving the atmosphere and re-entering. Many tests happened on different rockets, but they could never re-enter the atmosphere due to high speeds and intense heat. The failure of these vehicles were also due to hypersonic speeds, shock waves in the shock layer, and drag force. So the past history and involvements of the thermal protection system would be that, to continue on, in the late 1950s, Montgomery created the term thermal barrier and thought they had no materials at the time to stop vehicles from heating. Various thermal protection systems had been developed during the space race, and effective technologies have been new materials, accurate sensors, and effective modeling tools.
There are three types of thermal protection systems. It would be the passive method, the semi-passive method, and the active method. Down below, there's a chart that shows what falls under these methods. For the passive method, you have the heat sink, the hot structure, and the insulated structure. In the semi-passive method, you have the heat pipe and ablation. And then for the active method, you have the transpiration cooling, film cooling, and convective cooling. Now, for the passive method, it can be a hot sink, hot structure, or insulated structure, and they're normally used for small heat pulses. So for the heat sink, it's a metal structure with high heat storage capability, and it's generally used for short heat pulses. And then for the hot structures, it allows effective radiation when the surface temperature reaches a certain level due to high emissivity. Heat pulse here is not a concern. And then the third method would be the insulated structures that have an outer layer that reflects heat and an inner ceramic fiber layer that slows heat transfer. Now here is shown what falls under these structures. So the first photo here, you have a heat sink that's used for the GE MK2 re-entry vehicle. And as shown in each photo, you can see the surface heating entering on those structures and the radiation coming out of it, as well as the connection of each vehicle structure. And then for the second photo, you have the hot structure, which is used in the wings of X-15 made from Inconel X. And then for the third photo, you have an insulated surface used on the Evelyn on the space shuttle orbiter. And as you can see there, that it has an insulation that slows the heat transfer.
Moving on to the semi-passive method, there are two ways to cool down a vehicle, using heat pipes and abrasive surfaces. This picture below shows a simple diagram of how both of these methods work. Heat pipes are used to dissipate heat by phase change, while abrasive surfaces carry heat away using two methods, ablation or pyrolysis. Ablation focuses on eroding or vaporizing a material surface caused by high temperatures, while pyrolysis relies on the decomposition from high temperatures without using any oxygen. Heat pipes distribute heat through phase change. The diagram off to the side shows the heat source from the far left evaporating the fluid, creating a pressure gradient. As the fluid turns into a vapor, it will move on to the cooler sections of the heat pipe. This cooler section causes the vapor to turn back into a liquid through condensation, where heat flux is released outside of the heat pipe. However, disadvantage of heat pipes are extremely high heat fluxes, which can cause permanent damage to the heat pipe in a process known as dry out. There are three circumstances that causes dry out: boiling, capillaries, and the sonic limit. Made of composite materials such as carbon, glass, or organic polymers, these abrasive materials will react with gases or flux to oxidize, melt, or sublimate. Hot gases radiant flux or boundary shock layer heat the surface of an ablative surface. As the polymer decomposes, it leaves a char layer, where pyrolysis gases are formed. The boundary layer thickens as a result from the pyrolysis gases as it passes through. This reduces the convective heating. There are multiple types of surface removal: melting or fusion, vaporization, oxidization, sublimation, or platination. An application to abrasive surfaces was used during the Apollo command missions. NASA used a honeycomb structure made of steel, fiberglass, and epoxy resin as the heat shield for these missions. The shell of fiberglass vaporized or ablated as the vehicle re-entered the atmosphere, which prevented the heat coming through the crew compartment.
Moving on to the active methods, the first one is radiative cooling, which uses thermal radiation of materials in high temperature conditions. And this method requirements are strict and the amount of heat dissipated is very small. So this method isn't as effective and is not suitable for high wall heat loads. The second method is film cooling, which has two categories: liquid film cooling, which is for stabilization when used for high-speed environments, and gas film cooling, which is more common for hypersonic vehicles, because the heat insulation is usually used for low to medium speeds, and it has a simple structure with high performance. The third one is transpirative cooling or transpiration cooling, where the heat insulation method has a high cooling performance because the inflow air or the fuel could be used as a coolant. With this method, it has two disadvantages since it'll impair the engine performance and it is a more complicated structure, so it could lead to low structure reliability. The last one is regenerative cooling, which is an endothermic convective method, and the heat absorbed will not dissipate but instead be carried by propellants and returned to the combustion chamber. For the thermal protection system protocols, it starts off with the thermal protection systems development for entry, descent, and landing. This is the design, analysis, and testing of the system. So they start to analyze Simulations do independent modeling and model validations at this stage, and they make sure that it's up to standards or at the right specifications. To the right is an example of one of the analysis that they do for lift to drag of different vehicles, since the lift to drag is a very important component of thermal protection systems. The second step in thermal protection systems is the facility, and this is where the materials are manufactured, installed, and repaired. This facility provides the ovens for heat cleaning, sintering, and waterproofing the materials used to making the systems. The third step in this is the charring ablator response. This is where the facility supports the vehicle designs, ground testing, and flight data simulation. It is used to simulate reusable and ablative thermal protection systems. And the last step is the actual testing in the radiant heating test facility. This is where they test the capabilities of the thermal protection system and simulate the heating experienced by spacecraft entering the atmosphere in a controlled environment. They simulate the thermal entry thermal profiles, thermal gradients, and pressures. To the right is the layout of a radiant heat test facility at the Johnson Space Center.
Right. To reiterate, thermal protection systems is crucial for rocket design and mission retrievals. These systems provide safety for rockets to re-enter our atmosphere. First introduced in the 1920s and successfully developed in the 1950s during the space race, thermal protection systems is a crucial subject when it comes to exploring space. Thermal protection systems is differentiated by three different types, which are passive method, semi-passive method, and the active method. And we discussed the various facilities and protocols needed to clear and test any of the thermal protection systems types for spacecraft missions that require re-entry. These are the thermal protection system development for entry, descent, and landing, the thermal protection system facility, the charring ablator response, and the radiant heating test facility. Here are references. One of them is from NASA, and the other one is a research paper discussing everything about the thermal protection systems. All right, thank you. Any questions?
Okay, that was my bad. I thought you were just gonna say these are references.
It's okay.